Hello everyone, my name is Wouter Pere. I'm the founder and main developer of GHEtool, and in today's video we're going to continue our discussion on designing combined active and passive geothermal cooling systems with GHEtool. So in the last video we talked about the more theoretical background of this topic, and today I want to go through an example in GHEtool together with you, so you feel empowered to do the same with your own project. So let's get into the slides. So to recap, last time we talked about the difference between active and passive cooling. With passive, or also sometimes called free cooling, is the preferred way of cooling your buildings with geothermal borefields, because there is no compression step needed. But the problem is that it requires quite a big borefield, because you have a very strict maximum average fluid temperature. Because if you want to cool your buildings passively, the temperatures of your fluids cannot exceed the 18 degrees Celsius maximum limit, because otherwise you won't have the cooling capacity needed in order to cool your building. And you can solve this problem by going for an active cooling, so actually using your heat pump and the compression step to cool your buildings in an active way. This way there is no real limit on the maximum average fluid temperature, because the heat pump is working to get you the cooling, and this makes sure that you can decrease the borefield size when cooling. The problem is that there is electricity consumption, and the main design question we had was, can we combine the sizing when we use active cooling with the efficiency of passive cooling? And last time we talked about an example with an auditorium, and today I want to show you an office building in GHEtool, which is a totally different building, where you can see that we have, it's quite a big office, up to 380 kilowatts of cooling demand, with also quite a lot of full load hours. There are quite a lot of internal gains in an office, quite a lot of computers, in this case I think even a small server room, and we have also a heating demand which is a little bit lower than the cooling demand in this case. So let's get into GHEtool, and I'm gonna show you how you can size a borefield for this particular building. So here we are in GHEtool. I created a new project, and we're going to populate it with the data we need for this simulation. So for the ground data, I'm just going to leave it for the default values for now. Then the borefield tab. Now typically for your own project, you will not know this in advance, but because I prepared for this video, I know that I will need 10 by 13 boreholes, so just for time's sake I will start with this borefield, but for your own project you have to do it with trial and error to come up with a design that works for your project, but I know that 10 by 13 boreholes will work for me. The borehole resistance is, we're going to use a double U-tube, DN32, with 30% of monopropylene glycol and 0.2 liters per second as our flow rate. And then in our thermal demand, which is the most important, that we're going to load a CSV file. Every time you're working with this methodology of combining active and passive cooling, you will need a building with an hourly heating and cooling demands in order to be able to work with this methodology. So this is the file we have out of our dynamic simulation with heating and cooling load. Let's go ahead and open it, and in our case the columns are the other way around, and we import this load. So now I'm just going to calculate it, and we will end up with our temperature profile for the situation in which there is no active and passive cooling, and with the SE here of 20, we're going to get a result for our passive cooling, or 100% passive cooling. And this is the result. So what we can see that we have indeed 130 boreholes, and we have a temperature profile which is more or less in balance. We have an imbalance in the injection, so it's injection dominated. It means it heats up year after year. And as you can see, strictly speaking, we're not always below the temperature threshold. But if you zoom in on that one particular peak, you see that it's just a couple of hours in which we're above. So in my opinion, it's not worth it drilling a couple of boreholes more in order to get also that peak below the 17 degrees temperature limit. So in my opinion, this borefield is well designed for passive cooling. But as you can see, we have quite a lot of temperature below the 10 degrees Celsius. So this borefield is really sized for the cooling capacity, which leaves us with almost 20,000 meters of borehole length, which is quite a lot for this building. So what we'll try next is say, well, assume that we will do this in an active way. So we say, well, this temperature limit of 17 degrees, it's not feasible for our design. Let's crank it up to 25 degrees and use active cooling. So then we go to our thermal demand tab and we use, for example, 7 as the efficiency for active cooling. Please check this with your heat pump you're using, but 7 is a value that can be used. 5 is a little bit more on the conservative side. 7 is perhaps a little bit more realistic, but it depends on your hydraulics and the temperature regimes. So now let's go ahead and estimate the amount of boreholes we will need. So let's say we halve it and we go for 7. So let's see what it gives with 70 boreholes if we calculate it now using active cooling. And this is the result we end up with. So we see that we are always below the 25 degrees. So perhaps I'm just going to check. If we go for 6, what will that give us? And this is the result if we go for 60 boreholes. Here you can see that we indeed do cross the temperature limit, but I would guess that it's the same peak as before. Yeah, okay. So in my opinion, we can work with 60 boreholes for this particular building. But as you now can see, we are doing everything in a passive or in an active way. There is still quite a lot of cooling being done below the 17 degrees in which we can do things passively. So let's now go to the more advanced methodology of combining active and passive cooling. So we duplicate the scenario once again, and let's call it scenario 2 threshold. And let's indeed start with the threshold temperature method. So we go to thermal demand and we switch on active and passive cooling. So the passive cooling we stick at 20 degrees. Let's use 7 for active cooling and say, well, everything below 17 degrees we can do passively, but once the average temperature crosses the 17 degrees limit, we will switch to active cooling. Let's go ahead and calculate this. And here are the results. So we can see we have an average SEER of 11. Let's see, so the temperature looks more or less the same. But this is an interesting graph. So what you can see here, if we zoom in on our first year, for example, this is the cooling profile of our building. And in summer, quite a lot of high peaks are, of course, everything above the 150 kilowatts is for active cooling. But there is still quite some passive cooling in between. And as we scroll down, we see that in this case we can do 85% of the total cooling demand in a passive way, which is rather good, knowing that we came from 130 boreholes to do everything passively. We're now at 58% passive cooling, but with only 60 boreholes. And as you can see here, the amount, the SEAR, drops year after year, and the yearly share in active cooling increases, which is the opposite of what we said last video. So in last video we had an auditorium which was extraction dominated, so we extracted more energy from the ground than we injected in it. Here it's the other way around. So we have an injection dominated borefield design, because this office building has quite a lot of internal gains, for example, indeed a server room. And this makes it such that year after year, it's not quite that visible. Yeah, you can see it. The amount of passive cooling, it decreases because the ground heats up. So year after year, we can do less with our passive cooling. And that's why this share of active cooling increases year after year. So let's go ahead and try playing around with this a little bit. So let us say that we're going to work with a threshold and a bigger borefield. So now what we did is we worked with 60 boreholes, but we can of course say, well, we want a higher percentage of this passive cooling. And we can, for example, say, let's go to 80 boreholes. So a 30% increase in our borefield size. What will that give us in the end? Here we are now. As you can see, we are well below the 25 degrees temperature limit now. And this is because, well, we designed it such that we would reach this limit in a pure passive active cooling way. We're now way lower, meaning that we have also a way higher percentage of passive cooling. So as you can see, by just drilling 20 extra boreholes, we have 80% of our cooling in a passive way. You can still see here that the yearly share of active cooling, it increases year after year because the imbalance is still the same. But by going from 60 boreholes with only 75% to 80 boreholes, we can increase our geothermal share quite a lot. So the last thing I wanted to show you is, because we now worked with the threshold methodology, but as you can see, the cooling, or the highest cooling peaks, are in July and August for this particular building. So what we can do, for example, is that we go to the thermal demand tab and let's say, well, used fixed months, July and August, and calculate the result for this situation. And these are the results now. So, and the profile looks quite the same, but now there is a little bit of a difference, meaning especially since now in summer it's all active. So it looks a little bit the same, but there is no passive cooling now in this month, because we said, well, it will be active. And the share of passive cooling is more or less the same. It was 58% before, now it's 51, 52. So in this case, it's more or less the same, but the main challenge is, if you use this method, is that you do not actually know if you will be able to provide the cooling in a passive way, because you can see there are quite some high cooling peaks at the end of July, which are really hard to spot on the figure, but it will be somewhere around here. And there you do not know if they are able to do it in a passive way. So the disadvantages of this method, although it is faster and it gives a first good insight, is that you do not know if at the other instances you will be able to fulfill your demand in a passive way. which you do if you use the threshold method. So to summarize, let's jump back to the other scenario with the threshold. And here you have what I would say a good or an intelligent design. It of course all depends on your investment cost, your space, the TCO, the total cost of ownership, which we'll make a whole other video about in the future. But here you see that if we use 80 boreholes, we have an average SEER of 14, with 80% being passive cooling. And if we compare that to just our active cooling situation, there we had 60 boreholes with an average SEER of 7, and in our 100% passive case we have 130 boreholes. So by combining active and passive cooling, we are able to create a feasible system which will also work in practice and which will ensure the summer comfort. So I hope this video was interesting to you. I suggest you start playing around with it yourself for your project to really grasp the potential of going this deep into designing for summer comfort. If you think this video is interesting, please consider subscribing. It really helps us get this message all across the globe. If you have ideas for other videos, please let us know. We'll be more than happy to see if we can create an article on that subject as well. And I hope I can see you next time. Take care. Bye.